monthly car costs, payments, fuel, repairs, parking, and even that weekend-only second car, plus the constant worry about replacing parts every few years, are challenges every car owner knows too well. Are you seeing you there? But here's Tesla's 2026 solution. The Model 2, a compact EV designed to handle both weekday errands and weekend adventures in one single vehicle. With 19 features revealed, from interior comforts to exterior innovations and much more, this is Elon Musk's answer to eliminating the need for a backup car and the endless upgrade cycle. The Model 2 promises practical space, lower running costs, and hardware that stays relevant as software evolves. Curious about all the details and when you can get your hands on it? Keep watching. Subscribe and hit the notification bell to help AutoGearshift reach 16,567 subscribers. And be among the first to uncover all 19 features of the Tesla Model 2 before anyone else. 1. How does Tesla build the Model 2 to be the last car you need? The headaches of owning a car are not just about the sticker price. Tesla Model 2 is built to solve that. A city-friendly car that still handles weekday commutes and weekend loads. With fold-flat rear seats and a front trunk, Model 2 gives you enough space for tools, groceries, or luggage without keeping a second just-in-case car. On running costs, the advantage of an EV shows up mile by mile. Efficient EVs typically land around 4 to 6 cents per mile, while common gas cars sit around 10 to 13 cents per mile. Drive 1,000 miles a month, and that gap saves about $50 to $60. That is the basis for Tesla Model 2 to aim for one car does it all, while keeping monthly expenses lighter. Practicality also includes vehicle-to-load power. With a battery around 50 kilowatt hours, the Model 2 class can supply about 1 kilowatt continuously for roughly 50 hours, or 2 kilowatts for more than a day. That is enough for power tools, cooking while camping, or keeping a few essentials on at home during a short outage. Instead of hunting for a separate generator, your car becomes a mobile backup source. Home charging is easy to picture. With a 7.7 kilowatt level 2 charger, charging a 50 kilowatt hour pack from 10 to 80% takes about 4 to 5 hours. Plug in at night and it is ready by morning. A session like that costs only a few dollars and covers several days of commuting. The routine stays simple and does not disrupt your habits. Longevity is where Tesla Model 2 plans to go the distance. Tesla's approach leaves hardware headroom for years of software updates, and modules like cameras, screens, and sensors are separated so you replace only what fails. Modern battery chemistries reach thousands of cycles. If one real-world charge gets roughly 250 miles, the useful lifespan can add up to hundreds of thousands of miles. Industry research has even outlined pathways to million-mile cells under controlled conditions, which supports the idea that a Model 2 can serve for many years without forcing an early replacement due to rapid battery fade. Finally, upkeep is meaningfully lower. Independent surveys show EVs often cut maintenance and repair costs by about 40 to 50% compared with similar gas cars. Add that to the fuel savings above, and the total benefit can reach hundreds to over $1,000 per year, depending on how you drive. Put the pieces together, and a consistent picture emerges. Tesla Model 2 helps trim monthly spend, reduces time in the shop, and stretches the real-world service life of your car. Would you make the Tesla Model 2 your only car if it can keep home essentials running during short outages with vehicle-to-load power? If your answer is yes, comment Model 2 below. 2. In what ways does the Tesla Model 2 cut the financial baggage of owning a car? Tesla Model 2 is positioned as a lighter way to own a car from day one. The idea is to start with a base configuration to keep the entry cost low, then add features only when you truly need them. Over the long run, independent studies show EV owners typically spend about half as much on maintenance as comparable gas car owners. And energy costs are clearly lower, so your monthly outlay is easier to control when one car covers most daily needs. Tesla delivers the pay-as-you-need approach through software subscriptions. The FSD supervised package can be taken month to month at $99 in the United States, so you can turn it on for long trips or testing, then turn it off to avoid fixed costs. Beyond subscriptions, some performance upgrades are one-time purchases. For example, acceleration boost for the Model Y long range costs $2,000 and activates in the app, cutting 0 to 60 times without moving to the more expensive performance trim. Pricing models like these suggest Tesla Model 2 would also let you unlock when needed, instead of paying for everything up front. The entire ownership cycle is designed to be app-first. When ordering on Tesla's site, you pay a one-time, non-refundable order fee, then complete the remaining steps in the Tesla app, from uploading documents to tracking delivery. After delivery, you keep using the app to monitor charging, manage features, book service, and submit requests. Centralizing everything in one place cuts travel time and trims the small, hard-to-measure costs. Smaller paid add-ons follow the same pay-for-value logic. Premium connectivity is $9.99 per month, or $99 per year in the United States, so you can enable satellite maps and streaming when they add value, then disable them when they do not. From a household budgeting view, these items are easy to forecast and easy to trim, without affecting the core utility of the car. Put the pieces together, and the financial picture becomes clear. You lower the barrier with a base trim, add driving capability or conveniences by the month when needed. Buy a few one-time upgrades only if they feel worthwhile, and manage it all in one app to save time and incidental expenses. Combined with the reality that EVs generally cost less to maintain and to power over their lifetimes, Tesla Model 2 is presented as a car that does not carry financial baggage. You pay for what you use when you need it, while reducing the unpredictable costs that make many families hesitate to own a car. How would you choose for Tesla Model 2? Comment 1 if you want all features installed from day one, or comment 2 if you prefer the base model, then unlock features over time. 3. How could the Tesla Model 2 break from the normal car altogether? Tesla Model 2 aims for smartphone-style flexible ownership. You take delivery in an affordable configuration, then expand its capabilities through software only when you need to. The center of gravity is Tesla's over-the-air platform, which pushes new features, refinements, and fixes without a service visit. Community trackers such as TeslaScope have recorded hundreds of thousands of software installs across hundreds of distinct versions, a pattern that shows how frequently the ecosystem evolves. That cadence matters for a mass-market car. It means a Model 2 can ship with a focused feature set, meet daily needs on day one, and then grow with you over years without replacing the vehicle. The smart device idea is not just about adding menus or apps. It is about how the car prepares itself so you spend less time managing it. On current Teslas, you can schedule charging and set a ready-by time that aligns with off-peak electricity rates. You plug in once, the car handles the rest, and it is topped up when your morning starts. When you navigate to a supercharger, the system warms or cools the battery, so it accepts energy faster on arrival, which shortens each stop. A mainstream Model 2 inherits these behaviors, reducing small decisions that add friction to daily driving, from when to plug in to how to keep a road trip moving. Personalization also becomes infrastructure. The 2022.24 software introduced cloud profiles that carry your navigation favorites, media preferences, climate targets, driver assistance settings, and display layout. Step into any compatible Tesla in the household, and it feels familiar within seconds with the seat, mirrors, and interface, returning to your preferences. For families who share vehicles, or for owners who occasionally use a service loaner, this consistency cuts the new car learning curve to almost nothing, which is exactly what you expect from a modern device. Management lives in one app, which is more than a convenience. Ordering, tracking delivery, adding documentation, scheduling service, approving mobile repairs, viewing charging history, and buying or canceling software features all happen in the same place. Centralization shortens the time between wanting a capability and having it, and it turns many traditional ownership chores into quick confirmations on your phone. For a car that targets volume, this reduces overhead for both the owner and the service network, which translates into fewer surprises and fewer trips to a desk or a counter. Flexible ownership only works if the underlying hardware leaves room to improve. Tesla designs recent platforms with headroom in compute, sensing, and power management, so that software can do real work over time, not just change icons. A Model 2 that starts simple can later add driver assistance refinements, charging optimizations, or in-car conveniences as you decide they are worth the money. If your priorities change, the subscription switches off, and the base car keeps doing its core job. Put the pieces together and the picture is straightforward. A strong over-the-air backbone lets Model 2 improve on your driveway. Smart preparation trims time at the plug. Cloud profiles make any car feel like your car. And app-first management keeps the whole cycle tidy. This is not just a lower-priced EV. It is a way to make a car behave like a reliable piece of personal technology that respects your budget, your time, and your habits for years. Which Model 2 smart device feature would matter most to you? A. OTA updates that add features. B. Cloud profiles that make any Tesla feel like yours. C. App-first ownership for ordering, charging, and service. Drop your pick, A, B, or C. How does Tesla turn the Model 2 from personal car into shared asset with a tap in the app? Tesla has teased integrating ride-hailing and car-sharing directly into its application. That opens a path for Model 2 to serve your family first, then join a sharing or ride-hailing network when idle. Everything can be managed in one place. The market shows robo-taxis are no longer hypothetical. Waymo reports more than 1 million rides each month in Los Angeles, Phoenix, and San Francisco, and it recently launched a channel called Waymo for Business. Operating at that scale suggests autonomous taxis can run commercially in multiple cities, even if local rules advance at different speeds. To gauge the idea of earn while you sleep, look at how long cars sit still. Data from the United States Department of Energy indicates the average household vehicle is parked for approximately 95% of the day, so most capacity goes unused. Even if you let a Model 2 work only 2 evenings a week, the revenue potential is real. As a simple reference point, gross driver earnings in ride-hailing in the United States average about 23.33 United States dollars per hour before costs. 6 hours per week at that rate is roughly 140 United States dollars, or more than 550 United States dollars per month. This is a rough frame that excludes platform fees and your actual operating costs, but it shows what might be possible if Model 2 can participate in your area. Costs are the other side. The Internal Revenue Service standard mileage rate for calendar year 2025 is 0.70 United States dollars per mile for business use. This is not your personal cost, but it is a useful yardstick that bundles depreciation, maintenance, insurance, and energy. If average city speed is approximately 15 miles per hour, 6 hours of driving is approximately 90 miles, which maps to about 63 United States dollars when using the Internal Revenue Service rate. Compared with the rough revenue example above, there is a spread left to cover platform fees and your true depreciation. Results will vary by city, peak hours, platform pricing, and how you maintain the car. But this math helps set a floor price, so Model 2 does not run at a loss. If your city does not allow autonomous taxis yet, peer-to-peer sharing is the nearer path. Get around prices by the hour, with rates that can start around $5 and scale by vehicle and location, and the service bundle's trip insurance. On Turo, hosts typically keep between 65% and 90% of the daily rate depending on the protection plan, and the calculator tool estimates potential income by location, model, and market conditions. These benchmarks help you sketch a pricing plan if Tesla builds sharing into its own application, and they explain why the idea of list your car like a room is gaining traction. Transparent pricing and clear revenue splits make experimentation feasible. Looking ahead, the outlook is even more promising. If Tesla standardizes scheduling, smart routing, and remote vehicle checks, you could automate almost the entire workflow. You can turn on shifts for peak hours, lock out shifts when the family needs the car, and optimize pricing in real time as demand changes. Start small, measure real results, and then scale what works. Over time, the car can become a steady cash flow rather than a sleeping expense. That can support better insurance coverage, proactive maintenance, and longer battery life while maintaining a positive margin. For months, the Tesla community has been buzzing with speculation, but nothing compares to what just surfaced on Silicon Valley highways. A heavily camouflaged prototype, believed to be the Tesla Model 2, was caught in the wild, sparking heated debates across the automotive and tech world. What makes this sighting particularly significant is the timing and location. Testing on public highways at this development stage indicates Tesla's confidence in the platform's maturity. But here's what has industry experts pausing: the specific design choices visible even through the camouflage, the proportions that suggest radical manufacturing innovations, and testing patterns that indicate Tesla is validating technologies that experts haven't seen in production vehicles yet. And that's what we will unveil today. 1. How is Tesla deploying new battery integration patterns differently from their current lineup? Shift your attention to the rear quarter view in the second image, and something immediately stands out to trained eyes: the floor height relative to wheel diameter. The relationship suggests Tesla has fundamentally reimagined battery pack integration for this platform. Current Tesla models use structural battery packs, where the pack itself serves as a major chassis component, bonding between front and rear gigacast sections. This prototype appears to take that concept further, possibly implementing a cell-to-chassis architecture where individual battery cells bond directly to the floor structure, eliminating the intermediate pack housing entirely. The technical advantages of direct cell-to-chassis integration are substantial but complex. By eliminating the pack housing, Tesla removes significant weight and cost while actually improving structural rigidity. Individual cells, when properly bonded to structural elements, distribute impact loads more effectively than a packaged assembly because there's no intermediate structure to deform or fail. But the engineering challenges are profound. You're essentially making the vehicle floor out of hundreds of battery cells, each requiring precise thermal management, electrical isolation, and crash protection. The fact that this prototype exists and is being tested on public roads suggests Tesla has solved these integration challenges. Look carefully at the lower body side panels where the camouflage meets the rocker panel. The smooth, continuous surface suggests no conventional battery pack lip or mounting flange, hallmarks of cell-to-chassis integration. In traditional structural packs, you need robust mounting interfaces to transfer loads between pack and chassis. Direct cell integration eliminates these interfaces, saving weight and reducing assembly complexity. But it also means Tesla must manage thermal expansion across the entire floor structure, ensure uniform cell compression throughout the vehicle's service life, and design crash structures that protect cells without traditional pack armor. The solutions to these challenges represent genuinely novel engineering. The wheelbase to overall length ratio visible in these images suggests another battery innovation: higher volumetric packaging efficiency. By eliminating pack housing and optimizing cell arrangement for this specific platform, Tesla likely achieves greater energy capacity within the same floor area. Industry estimates suggest cell-to-chassis integration can improve volumetric efficiency by 15% to 20% compared to packaged approaches. For an affordable vehicle targeting a 250-mile range, that efficiency gain might mean the difference between viable economics and impossible compromises. You're looking at the same usable capacity with fewer cells, lower cost, reduced weight, and improved performance. Consider the charging implications. The prototype's testing patterns suggest validation of high-voltage architecture, possibly Tesla's 800-volt system currently exclusive to Cybertruck. This is a technology that enables faster charging speeds and more efficient energy use. Higher voltage enables faster charging with smaller, lighter conductors, but requires different cell chemistry and thermal management approaches. The camouflage around the charge port area shows additional bulk compared to Model 3, potentially hiding 800-volt charging hardware and enhanced thermal conditioning systems. If Tesla implements 800-volt charging on an affordable platform, it fundamentally changes the value equation. Suddenly, your Model 2 charges as fast as six-figure performance EVs, eliminating a major differentiation point between budget and premium segments. The implications extend beyond individual vehicle performance. Cell-to-chassis architecture requires different manufacturing processes, supplier relationships, and quality control approaches. Tesla must validate not just the engineering, but the entire production system's ability to consistently build thousands of vehicles with battery cells as structural components. This prototype testing represents validation of that entire ecosystem, including the manufacturing processes, supplier capability, quality systems, and service procedures. The fact that multiple prototypes exist and operate reliably suggests Tesla is close to production readiness with genuinely revolutionary battery integration. Does structural battery innovation change the fundamental economics of affordable AVS? If you see cell-to-chassis integration as the next breakthrough in electric vehicle design, comment "structural" below. The engineering elegance of making batteries serve multiple functions, such as energy storage, structural support, crash protection. This represents the kind of systems thinking that separates incremental improvement from revolutionary progress. And Tesla appears ready to bring this technology to mass-market vehicles. 2. What advanced driver systems are being validated through this real-world testing prototype? Now we arrive at what truly has industry experts puzzled. Look closely at the roofline in both images, particularly where it meets the windshield. That's not just camouflage bulk. The subtle protrusions and surface discontinuities suggest sensor integration for advanced driver assistance systems. But here's what's unusual. The placement patterns don't match Tesla's current camera-based vision system architecture. Something different is being tested here, and the implications could reshape Tesla's entire approach to autonomous capability. Tesla has long committed to a pure vision approach for autonomous driving, famously removing radar sensors from production vehicles. Yet recent Elon Musk statements acknowledge potential advantages of complementary sensor technologies for specific use cases. The prototype's roofline geometry suggests integration points for either additional camera perspectives, higher resolution imaging systems, or, controversially, possible LiDAR validation testing. Before skeptics dismiss this, remember that testing competing approaches doesn't mean production implementation. Tesla might be validating vision-only performance against sensor fusion benchmarks to build confidence in their approach, or identify edge cases where additional sensing modalities add value. The front fascia detail visible through the camouflage reveals something equally intriguing: what appears to be a more sophisticated front camera array than current production vehicles. The spacing and positioning suggest Tesla may be implementing stereo vision for improved depth perception, particularly critical for affordable vehicles that need robust performance without premium computing hardware. Stereo camera systems, while computationally simpler than monocular depth estimation, require precise calibration and can provide more reliable distance calculations in challenging conditions. For a mass-market vehicle where sensor costs must be minimized, stereo vision might offer the optimal balance between capability and affordability. But the real revelation is in what you cannot see directly: the computing architecture required to process all this sensory information. Tesla's current Hardware 4 platform represents substantial processing capability, but future hardware generations will need even greater efficiency to enable autonomous features at affordable price points. The prototype's testing patterns, particularly in the highway scenarios captured in these images, suggest the validation of not just sensors, but the entire perception-to-action pipeline. Tesla needs to prove that affordable computing hardware can process sensor data fast enough to enable safe autonomous operation across all driving conditions. Every mile this prototype accumulates feeds training data and validates algorithm performance on production intent hardware. The sensor positioning also reveals Tesla's thinking about feature availability at launch versus over-the-air capability growth. By implementing hardware capable of advanced autonomous functions, Tesla can deliver the vehicle with basic driver assistance features and progressively unlock capabilities as software matures. This approach has defined Tesla's strategy for years, but implementing it on an affordable platform requires even more careful hardware-software co-design. The sensors you're seeing integrated into this prototype must support not just current feature sets, but unknown future capabilities that will emerge from ongoing AI training. That's a remarkable hardware specification challenge when every dollar of cost matters. Consider the validation implications. Tesla isn't just testing sensors. They're validating the entire autonomous driving stack on production representative hardware in this prototype. Every scenario this vehicle encounters feeds into training datasets. Every sensor anomaly informs hardware specifications. Every software iteration proves out computational requirements. By the time this vehicle reaches production, Tesla will have validated thousands of hours of autonomous operation on exactly the hardware that customers will purchase. That's a level of real-world validation that most automakers achieve only after production launch, if at all. And it's why these seemingly mundane highway test images actually represent crucial milestones in affordable autonomous vehicle development. Can vision-based autonomy truly scale to mass-market vehicles without compromising capability? If you believe sensor technology is the key enabler for widespread autonomous adoption, comment Vision to share your perspective. The debate around sensing modalities will define autonomous vehicle capabilities for the next decade, and Tesla's approach with this affordable platform might settle some long-standing controversies once and for all. 3. How does the new unboxed architecture transform traditional vehicle assembly? Looking at these highway test shots, the first technical revelation isn't what you can see, it's what the proportions tell us about what's underneath. The prototype displays a notably shorter front overhang compared to the Model 3 or Model Y, while maintaining what appears to be a substantial wheelbase. This specific geometry isn't aesthetic preference. It's the physical signature of Tesla's unboxed manufacturing process in action. Traditional vehicle assembly requires body panels to wrap around a sequentially built structure, necessitating certain dimensional compromises. What we're seeing here suggests Tesla has eliminated those constraints entirely. The unboxed process fundamentally reimagines how vehicles come together. Instead of a single moving assembly line where the car gradually takes shape, Tesla builds major subassemblies in parallel, including the front module, rear module, battery pack, interior capsule. Each is optimized independently before final integration. The technical advantage is profound. Each module can be engineered to its performance limits without compromising other systems. Notice in the front quarter view how the wheel sits push toward the vehicle's corners. This isn't just about aesthetics. It indicates the front module likely integrates the motor, suspension, thermal management, and crash structure as a single pre-validated unit. Traditional assembly cannot achieve this level of integration density because workers need access from multiple angles throughout the build process. The real innovation becomes apparent when you consider manufacturing scalability. Tesla claims the unboxed process can reduce factory footprint by 40% while increasing production speed. How exactly to achieve that? By eliminating the sequential bottleneck. In traditional assembly, every station must complete its work before the vehicle moves forward, meaning your entire production rate is limited by your slowest station. With parallel sub-assembly construction, each module can be built at optimized speed, stored briefly if needed, and integrated only when all components reach readiness. The prototype's design specifically accommodates this approach. Notice how the camouflage breaks at certain vertical planes, likely corresponding to module separation points. But here's what industry analysts are debating. The thermal management integration visible even through camouflage. Look at the lower front fascia in the first image. Those aren't conventional air intakes. The geometry suggests active aero shutters integrated directly into the structural module. The suspension mounting points visible through the wheel wells tell another story. The attachment geometry suggests multi-link rear suspension, typically reserved for premium vehicles due to complexity and cost. Why would Tesla use expensive suspension architecture in an affordable car? Because the unboxed process allows them to build the entire rear suspension module, including links, bushings, dampers, and mounting structure, as a single subassembly that drops into the vehicle in one operation. The assembly time savings offset the component cost premium while delivering superior ride quality and handling dynamics. This is engineering optimization at system level, not component level, exactly what unboxed manufacturing enables. Is advanced manufacturing integration the key to affordable EVs without compromise? If you believe parallel assembly processing will define next-generation automotive production, drop the word modular in the comments. This architectural approach doesn't just reduce costs, it enables capabilities that conventional manufacturing physically cannot achieve. And what we're seeing in these prototypes is just the beginning. Tesla's approach with the Model 2 platform demonstrates that affordability doesn't require compromise when you're willing to reimagine entire vehicle systems from first principles. By building manufacturing processes, structural architectures, and autonomous capabilities specifically for mass market production rather than adapting premium vehicle approaches, Tesla is creating something genuinely new. Not just a cheaper EV, but a vehicle that delivers capabilities previously exclusive to premium segments at prices that enable widespread adoption. What you've witnessed in these prototype images isn't just Tesla's next product. It's a complete rethinking of how affordable electric vehicles can be engineered, manufactured, and equipped with advanced technologies. As these prototypes continue testing and validation, we'll keep analyzing every detail, every design decision, and every technical innovation that shapes this vehicle's development. Tesla just closed Q3 2025 with record numbers. 447,450 vehicles produced and 497,099 delivered worldwide. That is only the beginning. In 2026, the arrival of the Tesla Model 2 is set to push these figures even higher, as this car is poised to mark the end of China's EV dominance by combining a truly affordable price with driver-focused technologies that feel anything but cheap. 1. What makes the Tesla Model 2 outperform Chinese EVs in real-world driving? Tesla Model 2 delivers a punchy throttle feel because its motor is engineered for high torque per kilowatt and low loss, and the pieces of that design work together rather than in isolation. The IPM rotor uses ferrite assistance and carefully shaped flux barriers to blend magnet torque with reluctance torque while guiding flux along short, efficient paths, which trims iron loss as speed rises. That rotor is paired with a stator built from very thin electrical steel laminations of about 0.27 millimeters coated for low loss. Since eddy current loss scales roughly with the square of lamination thickness, moving from 0.35 millimeters to 0.27 millimeters can cut that component by around 40% when other factors are constant. Completing the picture, direct end-winding cooling through oil jets or slot channels raises allowable current density without pushing temperatures beyond safe limits, a change that often delivers double-digit gains in continuous torque, typically 10 to 30% depending on architecture. With these elements aligned, Tesla Model 2 snaps to the throttle at low speed, holds strong mid-range pull without chasing a higher peak rating, and converts more battery energy into motion rather than heat at cruising speeds. That same systems thinking carries over to braking, where efficiency and feel reinforce one another. Brake-by-wire measures pedal force and asks the motor for as much regenerative torque as conditions allow, calling on friction brakes only for the remainder. In everyday decelerations, this means regeneration handles most of the work, commonly 70 to 90% in urban cycles. The arithmetic illustrates why it matters. A 1.6-ton car at 50 kilometers per hour carries 154 kilojoules of kinetic energy, or 0.043 kilowatt hours. Recovering 70% returns about 0.043 kilowatt hours, 0.03 kilowatt hours to the pack. In stop-and-go traffic, these small wins accumulate and appear as a clear drop in WH per kilometer. In case you find the numbers and math feel overwhelming, click the link on the screen to learn more about Tesla's regenerative braking. I've already covered it in quite a detailed breakdown. Because regeneration is doing the heavy lifting, the friction hardware can be smaller without compromising safety. Trimming 1 to 3 kilograms of rotating and unsprung mass at each corner reduces wheel inertia, lets the suspension follow the road more faithfully, and makes the steering feel cleaner. This directly complements the motor's high torque per kilowatt, since more of the effort shows up as real wheel speed change rather than overcoming excess inertia. When the propulsion and braking systems work in concert, the road result is consistent and easy to predict. Tesla Model 2 jumps from 0 to 50 kilometers per hour quickly, keeps pulling on climbs because iron losses are suppressed and windings stay cool, and needs fewer kilowatts to make the same wheel torque in mixed driving. Each deceleration then returns a little more energy to the battery, lowering watt-hours per kilometer and extending range by a few percent in normal use, and even more in city traffic. The option to meet range targets with a smaller pack further reduces mass while preserving the lively feel. Heat loads in the motor and brakes stay lower, so acceleration and stopping remain stable through repeated cycles, pad and rotor wear slows, and pedal feel stays natural thanks to smooth blending. Low torque ripple from the thin laminations and optimized electromagnetics keeps the front end precise during lane changes or merges, which is exactly the kind of confidence drivers notice from behind the wheel. Which part of the Tesla Model 2 impresses you most? A. Snappy throttle and quick launches. B. Regenerative braking that lowers watt-hours per kilometer and extends range. C. Lighter brakes that make steering and body response smoother. Cast your choice, A, B, or C. 2. What makes the Tesla Model 2 go farther, weigh less, drive more smoothly, and have a lower total cost of ownership than Chinese EVs? Tesla Model 2 uses a silicon carbide inverter instead of an IGBT design. Silicon carbide supports higher switching frequency, tight power module integration with a very short DC bus that lowers equivalent inductance and resistance, and precise field-oriented control with accurate dead time compensation. Together, these choices let Model 2 travel farther, weigh less, feel smoother, and deliver a lower total cost of ownership than many Chinese EVs that still rely on IGBT hardware. Why does the Model 2 go farther? Higher switching frequency makes the phase currents closer to sine waves, so current ripple falls and both iron and copper losses in the motor drop. Silicon carbide devices also incur much lower switching loss at the same voltage, so the inverter burns less power as heat. Real-world gains of roughly 1.5 to 3.5 percentage points in inverter efficiency are common, and overall drivetrain efficiency often rises a few more points thanks to cleaner currents and accurate FOC. In urban cycles where the car spends most of its time at partial load, this improvement shows up as a 3 to 8% reduction in WH per kilometer depending on conditions. With the same battery size, Tesla Model 2 delivers more watt-hours to the wheels and covers more distance, or it can hit the same range with a smaller pack. Why is the Model 2 lighter? Lower loss means less heat to reject, which allows smaller heat, sinks, radiators, and pumps. The ability to switch faster also enables smaller inductors and capacitors. When the power stage is packaged as compact half-bridge or full-bridge modules with a short DC link, the inverter shrinks and can be mounted closer to the motor to shorten the DC path. For a small to mid-size car, these optimizations can remove roughly 4 to 10 kilograms from the drivetrain. Less mass improves energy use and gives the chassis a more agile baseline. Why does the Model 2 feel smoother? Lower phase current ripple produces smoother shaft torque, so throttle response feels natural even at low speeds. A short DC bus with low stray inductance cuts peak dV/DAT and switching overshoot, which reduces electromagnetic interference and the faint electric whine heard in some load ranges. Field-oriented control with accurate dead time compensation keeps the current vector locked on target, so torque does not dither with the PWM cycle, and transitions between drive and regeneration feel seamless. Drivers experience clean acceleration, predictable regen, and steering that is not disturbed by torque ripple. Why is the total cost of ownership lower? Energy is the first lever. If a car in this class consumes about 15 kilowatt hours per 100 kilometers, saving only 5% trims 0.75 kilowatt hours per 100 kilometers. Over 100,000 kilometers, that is roughly 750 kilowatt hours, worth hundreds of dollars depending on electricity prices. Hardware and maintenance are the second lever. A smaller inverter and cooling loop mean less material, lower mass, and fewer items to service. Reduced loss and lower junction temperatures ease stress on power devices, improving durability and cutting the risk of early replacements. When higher efficiency enables a smaller battery for the same range, weight and cost benefits compound again. Tesla Model 2 goes farther because less energy is lost in the inverter, and motor is lighter because power electronics and cooling can be scaled down, feels smoother because clean phase currents and precise FOC keep torque steady, and is cheaper to own because both watt-hours per kilometer and component wear are reduced. All of it flows from choosing a silicon carbide inverter over an IGBT design. 3. How is the Tesla Model 2's battery more flexible and optimized than the batteries used in Chinese EVs? Tesla Model 2 follows a cell-agnostic philosophy, which means a single battery pack can accept multiple cell chemistries without needing a full redesign. This approach lets Tesla choose the right chemistry for the use case and for local cell pricing. For example, LFP is inexpensive and durable. LMFP raises energy density on the LFP base. NMC provides longer range, and sodium ion is very low cost for urban duty. The ultimate goal is to lower cost per kilowatt hour by market, while still delivering the driving performance users expect from Tesla Model 2. To make that possible, the pack hardware is standardized from the start. Cooling channels and bus bars share one common layout, and the module frame keeps the same mounting footprint. When changing chemistry, engineers only swap spacers or pedestals rather than altering major structures or production tooling. Capacity is also tiered, for example, 32, 38, or 44 kilowatt hours, so each market gets a configuration that fits daily commuting or highway needs. This avoids carrying excess capacity that would only add weight and cost. In parallel with the hardware, the battery management system is crucial so each chemistry operates at its optimal limits. The BMS in Tesla Model 2 stores multiple profiles, including the OCV curve versus state of charge, temperature-dependent internal resistance, algorithms for estimating SOC and SOH, and C-rate limits for charge and discharge. When switching from LFP to LMFP or NMC, engineers simply load the appropriate profile so the charger and inverter apply the correct power and thermal limits. As a result, two Model 2 cars with different chemistries can deliver similar acceleration feel, similar charging behavior, and comparable life within the design envelope. Because most adjustments happen in software, update cycles are faster and validation costs are lower than with hardware changes. From here, the competitive advantage becomes very clear compared with many Chinese models that are locked to a single chemistry. First comes flexible pricing and supply. Tesla can buy the cheapest and most available cells in each region and install them in the same pack, keeping cost per kilowatt hour low, even when the market shifts. Next is performance matched to context. A city-focused car can use a smaller pack with LFP or sodium ion to optimize cost per kilometer, while a highway or cold climate version can increase capacity and use LMFP or NMC to preserve range and power. Finally, there is speed of launch and upgrade. When a new cell generation appears, Tesla only needs to integrate a new BMS profile and make small mechanical tweaks, which shortens time to production and reduces supply chain risk. The result is that the Tesla Model 2 does not depend on a single cell source. It consistently finds the best balance of cost and performance for each market, while avoiding unnecessary battery mass, which lowers total vehicle weight and improves efficiency. Drivers benefit through both range and ownership cost, and manufacturing benefits through faster rollouts and more stable supply. This is a practical technical difference that makes the Model 2 pack more flexible and more optimized than many competitors from China. Do you like the Model 2's cell-agnostic battery that can switch between LFP, LMFP, NMC, or sodium ion to keep costs low without hurting performance? Comment Model 2 wins if this flexibility is the feature you value most. 4. How is the Tesla Model 2 more stable, more efficient, and more adaptable across all climate conditions than Chinese EVs? Tesla Model 2 feels more stable and more efficient because it uses a unified thermal loop for the battery, the drive unit, and the cabin instead of 3 separate loops. The loop combines a shared coolant circuit, a central heat exchanger, electronically controlled multi-port valves, and a bidirectional heat pump. The ECU coordinates valve positions and pump speeds, so heat made in one place is routed to where it adds the most value. Less energy is dumped to the air, and more is recycled inside the car. This design cuts electricity used for heating and cooling. When the motor or inverter runs hard, the loop harvests part of that waste heat to warm the battery or the cabin, instead of switching on a resistive heater. During fast charging or high discharge, battery heat is reused for cabin conditioning. Because the heat pump has a high coefficient of performance in both directions, HVAC draw and thermal losses typically fall by about 10 to 15% in watt-hours per kilometer. With the same battery capacity, Tesla Model 2 travels farther. If range is fixed, it can meet it with a smaller pack that also lowers total mass. The loop also improves powertrain efficiency by keeping the battery in the golden temperature band of roughly 20 to 35 degrees Celsius. Cells have lower internal resistance there, so they deliver and accept higher current with less loss. The same pedal position produces more wheel torque and quicker response. Meanwhile, the loop continuously removes excess heat from the drive unit, letting the inverter and motor operate near their efficiency sweet spots. Together, these effects lift overall drivetrain efficiency by roughly 2 to 3%. The benefit is even clearer in harsh weather. Many budget Chinese EVs keep split loops and rely on resistive battery heaters, which slashes efficiency at -10 degrees Celsius or above 35 degrees Celsius. Tesla Model 2 pairs its two-way heat pump with predictive battery preconditioning that warms or cools cells before a fast charge. That reduces lithium plating, keeps charge power stable, and extends cell life. In real winter or hot summer driving, usable range can be higher by up to 20 to 25%, and the cabin reaches a comfortable temperature faster. That is why Model 2 can bend the market. Efficient drive, SiC power, a flexible pack, and a smart thermal loop working in harmony. Do you know someone who thinks Chinese EVs are unbeatable? Tag them and type "watch this" to prove it. Have you ever queued for ages in a mall parking lot just to wait for a free charger? Living in an apartment, timing off-peak hours every night, yet still worrying about your electricity bill spiking? Canceled road trips because you were not sure the stations along the route would deliver full power? And now that the $7,500 tax credit closed at the end of September, are you asking, when will there finally be an EV cheap enough for the majority? On Sunday, Tesla dropped a 9-second teaser ending with October 7th, 2025. 1. How can the Model 2 redefine how cars are built? Unboxed Assembly 2.0 is the foundation that lets Model 2, a simplified Model Y, cut costs while raising quality. In Unboxed 1.0, the car was split into only 3 to 4 large groups, work moved linearly, inspections were batch-based, and the slowest station gated the whole line. Unboxed 2.0 fixes those limits by standardizing 6 modules: body structure, interior, battery pack, drive unit, glazing, and exterior. These 6 modules are built in parallel and then married at the end of the line, so bottlenecks are removed at the process design stage. From that structural change, the metrics move decisively. Total takt time drops from about 10 hours to 4 to 5 hours, while a comparable Unboxed 1.0 setup typically bottoms out around 6 to 7 hours. As takt time falls, scheduling shifts from push to pull at each island, and the marriage order is optimized in real time by software, which sharply cuts interstation waiting and balances workloads. Cycle time reduction then pulls down work in process. In practice, Model 2 removes roughly 40 to 60% of in-process inventory. The factory footprint per vehicle shrinks by about 30 to 40% because there are fewer long conveyors and overhead robots. With less heavy infrastructure, capital per vehicle falls by an additional $1,000 to $1,500 in an optimized scenario. Dimensional accuracy is locked by in-station metrology. Each module passes a 3D scan gate using laser or blue light. The point cloud is compared to CAD, and deviations are compensated in the robot controller. Critical points such as suspension mounts, powertrain mounts, seat bases, and door hinges are held within plus or minus 0.2 millimeters. Compared with Unboxed 1.0, which relied on per-shift checks with CP and CPK, often around 1.0 to 1.2, to Unboxed 2.0 lifts CP and CPK for key dimensions on Model 2 to 1.3, 3 to 1.67, pushes first time right above 98% versus 94 to 96%, and cuts rework to 2 to 3% versus 5 to 7%. The result is tighter panel gaps, lower wind noise, and about $50 to $100 less per car in assembly-related warranty cost. In parallel, the role of large castings is redefined. Model 2 applies high-vacuum aluminum die casting with a large shot chamber to produce one-piece front and rear structures, with the option to integrate part of the floor. This replaces stamped and welded assemblies with 1 or 2 cast parts, removing more than 300 components and eliminating thousands of spot welds. Alloys with 8 to 12% elongation plus in-die quenching let many castings skip T6 heat treatment with shot cycles of 120 to 180 seconds. As a result, underbody and floor mass drop about 15%, torsional stiffness rises 12 to 20%, and crash load paths are embedded in the casting geometry to distribute forces into rails and box sections. The key difference from Unboxed 1.0 is where gigacasts sit in the locating scheme. Previously, they were add-on modules that still needed intermediary fixtures. Unboxed 2.0 standardizes gigacast surfaces as primary datums for other modules. Higher geometric accuracy from vacuum and gate control lets modules locate correctly on first fit, which shortens alignment time and raises end-of-line repeatability. Put together, parallel modular build lowers cycle time. Lower cycle time drives down WACI and floor space. Inline metrology keeps tight tolerances without rework, and gigacasting reduces part count while raising stiffness. Through this compounding effect, Model 2 achieves lower assembly cost per vehicle, more consistent surface quality and NVH, and more room for aggressive pricing while maintaining margins. Which should Tesla prioritize on Model 2 for the biggest real-world gain? A. 6-module parallel build. B. In-station 3-dimensional metrology. C. Next-generation gigacasting. Share your thoughts below. 2. What makes Model 2 stronger than rivals even while cutting material cost? The core advantage comes from 3 technical layers spanning materials, power electronics, and a high-voltage architecture. Together, they raise power density, cut losses, and reduce component cost without sacrificing day-to-day performance. First is the rare earth-free motor. Model 2 uses a new magnet formulation and an optimized rotor magnetic circuit paired with an oil-cooled hairpin wound stator. By shaping flux paths and current waveforms, torque density increases by about 10 to 12% versus prior rare earth designs, while magnet cost drops and exposure to ND, PR, DY prices is reduced. In urban speed ranges, Model 2's machine efficiency holds above 94 to 95%. Faster torque response yields smoother average acceleration, and regenerative braking peak power rises by roughly 8 to 10%. Eliminating rare earths also stabilizes thermal behavior because demagnetization characteristics are controlled through materials and oil cooling, helping the car maintain performance over repeated thermal cycles. Next is a low SiC inverter. Instead of using all silicon carbide switches like many competitors, Model 2 adopts a targeted hybrid. SiC devices handle the high voltage, fast switching stages, while silicon handles baseload. This partitioning can reduce SiC content by 70 to 75%, yet still deliver 97 to 98% conversion efficiency in the primary operating region. A low inductance DC link and short gate paths reduce switching loss, while 16 to 24 kHz switching keeps electromagnetic noise down. The result is less heat to reject, a lighter heat sink by a few percent, and a meaningful cut in power electronics cost, all while preserving linear torque control at higher speeds. The final layer is an 800-volt light electrical architecture. Model 2 sets pack voltage around 680 to 750 volts. For a given power level, current falls and I²R losses drop by roughly 30 to 35% in cables and bus bars. That allows smaller cross sections, trims copper mass by about 20 to 25%, and shaves 5 to 8 kilograms from the system. On high-power DC chargers, Model 2 targets 10 to 80% in 18 to 22 minutes, with 275 to 320 kilowatts peak segments, while battery thermal management holds 25 to 35 degrees Celsius to keep internal resistance stable. At highway speeds, higher voltage means lower current, so the inverter and motor operate nearer their efficiency sweet spots, cutting real-world consumption by 5 to 7% versus a 400-volt package of similar power. Combined, these layers yield a tighter, more efficient drive unit. The motor inverter module drops 8 to 12 kilograms. System losses over a mixed drive cycle fall about 6 to 9%. And the bill of materials for eMachine Plus Power electronics decreases by double-digit percentages thanks to rare earth elimination and Sci-C optimization. For drivers, that translates directly into sharper short burst acceleration, stronger and smoother regen, stable fast charging, and a lower total cost of ownership for Model 2 compared with similarly priced competitors. 3. How does Tesla turn the battery into a spine so the Model 2 is lighter, cheaper, and goes farther? The key is making the battery a structural element. On Model 2, this starts with dry-coated electrodes, moves through a cell-to-chunk pack architecture, and is finished by Octovalve 2.0 with a next-gen heat pump. Together, these raise energy density, cut dead material, and keep the pack in its optimal thermal window. So Model 2 is lighter, cheaper, and longer range while maintaining stable fast charging. With dry-coated electrodes, Model 2 no longer relies on solvents such as NMP for the cathode or water for the anode. The active mix, conductive additive, and binder are calendared directly onto the foil, then compacted, so large dryers and solvent recovery systems are largely unnecessary. Eliminating those units cuts electrode line footprint by 30 to 50%, slashes drying electricity, and reduces capex. In operation, line speed can rise 2 to 3 times, coating and drying scrap falls, and electrode cost per kilowatt hour drops about 15 to 20%. For the LFP variant targeted for Model 2, higher coat weights remain controllable for adhesion and porosity after calendaring, keeping internal resistance low during high-power charging. The next layer is a cell-to-chunk pack. Model 2 removes the module frames, bonds cells directly into large chunks, and mounts them in a load-bearing pack case. The pack becomes both the energy source and a structural member of the floor. Deleting modules reduces dead volume, raising usable capacity about 6 to 8% within the same envelope, and trimming total pack mass by 10 to 12 kilograms versus traditional module packs. The structural pack, plus adhesives and closed cell fillers, lifts body torsional stiffness roughly 12 to 15%, improving suspension precision and NVH. Crash rails and crush zones are molded into the pack case, and fire spread barriers and thermal propagation inhibitors maintain safety if a cell vents. Thermal control completes the picture. Model 2 uses Octovalve 2.0 with a high-efficiency heat pump to unify cabin, battery, and powertrain loops via smart valves and heat exchangers. During DC fast charging, the system preconditions the pack to 25 to 35 degrees Celsius and holds that band throughout the session. Real-world charge time improves by about 15 to 20%, and high-power segments stay flat longer. In cold weather, the heat pump achieves about 10 to 15% higher COP than the prior generation, lowering energy used for cabin and pack heating and extending real-world range by 8 to 12%. At highway speeds, inverter and motor waste heat is harvested in a controlled way to keep pack temperature stable, preventing internal resistance spikes and keeping consumption low. Combined, these three pieces make the battery both an energy source and a structural spine. The end result is an affordable segment car with driving feel and total cost of ownership that outclass rivals still using conventional pack architectures. Do you believe this battery tech will actually break the market by making Model 2 lighter, cheaper, and longer range? If yes, drop Model 2 in the comments and add your city so we know where you want it first. 4. Is software the secret weapon that makes a $10,000 Model 2 perform like an $80,000 one? The biggest differentiator on Model 2 is software. Instead of relying on expensive sensors, Model 2 focuses on vision-only perception. The new version of the occupancy network uses a video transformer to comprehend a full 3D scene from multiple cameras at once, handling both static and moving objects. By learning directly from temporal image sequences, Model 2 detects small objects about 30% more accurately and spots pedestrians, motorcycles, and partially occluded items a few fractions of a second earlier than the previous generation. With better perception, decisions are more confident, especially at busy intersections, narrow alleys, and cluttered parking lots. For decision-making, Model 2 uses a self-training planner. It learns from real driving data and applies offline reinforcement learning to optimize goals such as safety, comfort, and trip time. Standardized route testing shows that steering interventions drop by about 40% per 1,000 kilometers, while longitudinal and lateral jerk decrease 15 to 20%, improving ride comfort. Smoother acceleration and braking also reduce energy loss, trimming city consumption by roughly 2 to 4%, and lowering Model 2's cost per kilometer versus similarly priced cars. To improve quickly without bloating data costs, Model 2 relies on next-generation fleet learning. On-vehicle software runs in shadow mode to detect hard scenarios, then uploads only short clips with high training value. Thanks to intelligent filtering, the volume of data transmitted and stored falls by about 60%, while the quality of the training set doubles because rare edge cases are selected more effectively. This shortens the update loop, so Model 2 receives frequent over-the-air improvements without raising Tesla's operating costs. All of this is packaged in Model 2's OTA pipeline. The car can receive new software in functional bundles, with feature flags enabling A/B tests on a subset of the fleet before wide release. Background self-calibration of cameras and inertial sensors keeps perception quality consistent over time. From the user's perspective, Model 2 keeps getting better after each update, from self-parking to urban driver assistance, without requiring additional hardware. Against competitors, Model 2's cost advantages in materials and assembly are amplified by software. Occupancy Network VNext sees more clearly, the self-training planner drives more smoothly with fewer takeovers, and fleet learning teaches the system faster at lower cost. Together, they deliver driving feel and driver assistance capability approaching premium cars, while Model 2's ownership cost stays accessible. This is how a roughly $10,000 car can deliver an experience comparable to $80,000 models that depend heavily on expensive hardware. This is the first Tesla designed to make independence affordable again, and it's doing so through three powerful breakthroughs that every driver can feel the moment they sit inside. What are they? And what makes them break the market and put an end to Chinese EVs? We will break it down now. 1. How does Tesla Model 2's dual motor setup handle every drive and provide steady control for seniors? Imagine merging onto the freeway in the rain with low visibility. You press the accelerator and the car responds instantly with smooth, confident, no wheel spin, no jerking. That kind of quiet control is what senior drivers have always deserved behind the wheel. But for the first time, it's available in a car that costs just $10,559, the Tesla Model 2. So how can having two motors, in front and rear, transform every drive into a composed, predictable experience, especially for drivers who value safety and control more than speed? The answer lies in Tesla's dual motor engineering, a system that's been tested and refined for years in premium models and now brought down to a level ordinary Americans can finally afford. According to the National Highway Traffic Safety Administration's 2025 reports on electric vehicle performance, dual-motor all-wheel drive systems like this improve traction by 45% on wet surfaces compared to single-motor setups. That's the same technology that's powered Tesla's higher-end models for years, only now it's being used to make everyday driving safer, not just faster. Each motor in the Model 2 uses high-efficiency copper windings to generate a combined 300 horsepower, allowing for seamless acceleration from city streets to freeways. This isn't a car that jerks forward or hesitates, it glides. Unlike some cheaper Chinese imports that rely on single motors, which is known to produce 20% more wheel spin in traction tests. Tesla's design distributes torque evenly between the front and rear axles. That balance is what gives the car its planted, predictable feel on the road. You don't have to fight the steering wheel. You simply steer, and the car does the rest. This dual setup isn't built for racing, it's built for real life. Or, in other words, it has a high practicality. In California, where hilly roads can reach 10% grades, the twin motors deliver 25% more climbing power, allowing smooth ascents without draining the battery. Over a year, that alone can save around $400 in extra energy costs for those living in steep areas. In New York's icy winters, it's proven to reduce skid-related incidents by 36%, giving peace of mind on slippery intersections. Down in Florida, with an average of 50 inches of rain per year, the Model 2's all-wheel drive improves hydroplaning resistance by 28%, a lifesaver for older drivers who face wet highways and sudden storms. And in Texas, where summer heat often hits 100 degrees Fahrenheit, Tesla's advanced cooling system keeps the dual motors operating at 92% efficiency, extending range by an extra 15 miles per charge, which is perfect for long errands or weekend drives. Put all that together, and the Model 2 delivers a 300-mile range on a full charge with 25% better regenerative braking efficiency, turning every stoplight into a small recharge. That means up to $500 saved annually in electricity costs, just from energy recovery. When you're living on a fixed income, those numbers add up. It's not just a high-tech upgrade, it's a financial cushion. For senior-heavy states like Florida, home to more than 4 million residents over 65, this could be a breakthrough moment. An EV that is affordable, weather-ready cars like the Model 2 can boost electric vehicle adoption in these areas by an estimated 18%, making sustainable driving practical for millions of retirees who've waited for an EV that truly fits their lifestyle. Do you remember those days when a bit of rain or a steep hill made you hesitate before heading out? That uncertainty fades with the Model 2. It gives you the confidence to keep your daily routine, picking up prescriptions, visiting family, or simply enjoying a quiet afternoon drive without worrying about traction, cost, or safety. The dual motors don't just move the car, they give back your sense of independence. So if a car could deliver that kind of control and peace of mind on every road you drive, would you call it the future or just smart engineering finally done right? Type dual motor in the comments if you believe this technology is the real turning point for affordable electric cars. Does this sound like the steady drive you've been waiting for? Stick around for the next part, because what Tesla has done with its supply chain will surprise you even more, and could explain how the Model 2 keeps your monthly costs lower than you ever thought possible. 2. How does Model 2's streamlined supply chain logistics offer tangible monthly savings? If every time a car company cut a production cost, the customer actually felt it, not as a discount on paper, but as money they could keep every single month, then Tesla might be the first one to make it real. That's exactly what's happening behind the scenes with the Tesla Model 2. This isn't a story about cheaper parts. It's a story about smarter logistics. Every decision Elon Musk made about the Model 2 supply chain was built around one simple question. How do you make a car that stays affordable long after you drive it off the lot? So how can reorganizing the way parts are built, shipped, and assembled across continents actually make your car payment, your maintenance bill, and even your electricity costs lower? The answer lies in Tesla's just-in-time regional sourcing system, a structure that's not just efficient, but revolutionary. The company has established 12 US vendor hubs for critical components, like wiring harnesses, reducing transit time from 15 days to just 3 days. That's a 35% cut in logistics costs compared to the overseas model used by most Chinese manufacturers, where average delivery times stretch to 45 days. Each Chinese-built electric car carries between $800 and $1,200 in supply chain fees before even reaching US ports. In contrast, Tesla's approach brings that cost down to about $500, passing an estimated $700 in savings directly to buyers. Here's how Tesla makes it happen. Watch closely. By standardizing 80% of all component codes, the Model 2 can pull parts from multiple domestic suppliers without waiting for customized imports. This alone boosts assembly capacity to around 1,200 units per day, a figure no imported competitor can match in this price class. The domestic content level for the Model 2 is an impressive 85%, meaning it avoids the 20% tariff hikes currently applied to Chinese-built vehicles. It's not just patriotism, it's a direct cost advantage that keeps American buyers from paying for overseas inefficiencies. For older drivers, this translates into something practical: lower maintenance costs and shorter repair times. Tesla's domestic chain allows on-demand part availability for essentials like brakes and sensors, making repairs 25% cheaper and cutting service downtime by 75%. Instead of waiting 3 or 4 days for a part to ship from overseas, many repairs can now be completed in under 24 hours. For Americans over 65 who drive about 8,000 miles per year, this saves roughly 30 hours annually, time that can be spent on hobbies, family, or simply enjoying the drive. The Model 2's connected service app even predicts part wear before breakdowns happen, sending early alerts that prevent costly surprises, a major advantage for retirees living in rural areas far from service centers. Meanwhile, most Chinese automakers still depend on multi-tier supplier webs and ocean shipping to reach the US, adding both time and tariff exposure. Even with lower labor costs, their export logistics still add $800 to $1,200 per vehicle. Tesla's domestic approach eliminates those fees completely. In simple terms, Chinese manufacturers compete on low wages. Tesla competes on zero friction. And in a market where buyers watch every dollar, that difference isn't small, it's the whole game. When you're living on a fixed income or a social security check, $5,000 saved over a few years isn't just a financial detail, right? It's a month's worth of groceries, medication, or gas money for a visit to the grandkids. That's why Tesla's efficiency revolution hits home. It's not corporate streamlining, it's real economic relief. Elon Musk's logistics shakeup is designed so that ordinary people feel the benefit month after month. So if a company can take the same car you already want and make it $700 cheaper before you even drive it. Would you call that marketing, or would you call that proof that efficiency finally pays off? Type $10,559 in the comments if you believe that this new price point is where Tesla starts rewriting what affordability means in America. 3. How is the integrated precision steering mechanism offering seniors effortless handling in daily traffic? Probably you've felt that small moment of tension before. As you are turning the wheel into a tight parking spot, or merging across lanes when traffic's thick and fast. Your shoulders stiffen, your grip tightens, and you hope the car responds just right. Now imagine that same motion becoming light, steady, and smart enough to anticipate your next move before you finish turning. That's what Tesla's new integrated precision steering mechanism brings to the Model 2, designed not for racers, but for everyday Americans who want safety, comfort, and confidence behind the wheel. So how can a steering system built on sensors, adaptive feedback, and electronic mapping turn daily driving from effort into ease, especially for seniors who are done wrestling with the wheel? The secret is real-time engineering that blends precision mechanics with intelligent software. The Model 2's steering adapts instantly, whether it's tight city parking in Florida or smooth highway cruising in Texas. The first piece of this technology is the variable electronic steering ratio, which automatically adjusts how much the wheel turns relative to the tires. At low speeds, like in parking lots, the system tightens to a 10-to-1 ratio, meaning a small hand movement turns the wheel sharply, cutting steering effort by 35 to 50% compared to a standard mechanical setup. At highway speeds, the ratio stretches to 20-to-1, creating smoother, steadier lane control that keeps the car balanced even in crosswinds. Tesla's electronic control unit processes signals at 1000 Hz, recalculating thousands of times per second to deliver consistent, natural feedback. You're not fighting the steering is quietly reading your movements and adjusting to make them effortless. Then comes adaptive motorized feedback, Tesla's real differentiator. Instead of relying on a single hydraulic pump like old systems, the Model 2 uses dual redundant electric actuators connected to both the steering column and wheel sensors. They detect micro movements, even a slight tremor in your hand, and respond within milliseconds. This allows the system to smooth out uneven pavement or correct for strong side winds automatically. In practical terms, this results in about 40% smoother lane centering and 25% faster correction during sudden maneuvers, according to internal studies on steering control systems. The wheel doesn't jerk or resist, it flows with your intent. The system also integrates directly with Tesla's autopilot vision, creating what engineers call a predictive lane helper. The steering communicates constantly with the car's cameras, ultrasonic sensors, and artificial intelligence mapping software. If the vehicle senses a slight drift or misalignment, it gently adjusts before you even realize what's happening. Data from vehicles equipped with similar sensor-based steering systems show up to a 38% reduction in unintentional lane departure, which is a crucial improvement for senior drivers whose reaction time may be slower. It's like having a co-pilot that silently watches your surroundings and keeps you safe without taking away your control. But perhaps the most noticeable benefit comes at low speeds, as what many older drivers call the parking struggle. The Model 2's steering motor can provide up to 250 Nm of assist torque below 10 miles per hour, making wheel turning nearly 50% lighter than older power steering designs. Paired with the 10-to-1 ratio, it allows easy one-handed parking, even for drivers with a mild arthritis or limited shoulder mobility. For seniors in crowded cities like Los Angeles or New York, where tight spaces are part of daily life, this is more than what is called as convenience. Underneath all that innovation is a built-in fail-safe system that keeps control secure at all times. Tesla's dual controller design ensures that if one electronic circuit fails, the other takes over instantly. It even includes a battery-backed mechanism that maintains steering power during temporary outages. With a 99.9% steering availability rate, the Model 2 system operates at reliability levels comparable to aviation-grade standards. That means even in a rare malfunction, drivers retain full steering capability through mechanical fallback. No risk, no panic, just confidence. And because it's fully electric, the maintenance savings are real. No more hydraulic fluid leaks, no pump failures, and no belt replacements. Over the car's lifetime, this simplicity reduces steering maintenance costs by 60%, saving around $300 to $400 per vehicle. For retirees managing tight budgets, that's not just an engineering stat. It's a little extra breathing room every year. If you've been wondering how Tesla can sell a car this advanced for the price of a used Honda or a new BYD Seagull, this video will show you the side of the story no headline ever mentions, the hidden engineering shifts, the quiet cost revolutions, and the reason this little car could redefine how every American family owns a vehicle. Stay with me to see how the Model 2 secretly becomes a test for the future of US industry, and why it may end the inflation itself. 1. How does Tesla actually make an $11,555 price point possible without destroying profit margins? Here's the part that separates real engineering from marketing fantasy. Traditional automotive assembly involves building a car in sequence. You construct the frame, drop in the powertrain, add the interior, attach the exterior panels, all in a linear progression that requires massive factory footprints and armies of workers performing sequential operations. Tesla's unboxed manufacturing for the Model 2 demolishes this paradigm entirely. Instead of assembling the vehicle as one continuous unit moving down a production line, the car is divided into large sub-assemblies that are completed simultaneously in parallel workstations. The front section, rear section, underbody, and side panels are finished independently with all wiring, components, and features fully installed before final integration. This isn't just faster, it's geometrically more efficient because you're multiplying workforce productivity across parallel operations rather than adding it sequentially. The mathematical reality is striking. Traditional assembly requires approximately 30 hours of labor per vehicle, with workers accessing cramped spaces inside a partially built car. Unboxed manufacturing drops this to roughly 15 hours because technicians work on flat accessible modules where every component is within easy reach. When you're targeting production volumes of 2 million units annually, that 15-hour difference translates to needing half the factory workers, half the physical space, and dramatically reduced capital expenditure per unit of production capacity. For context, a traditional automotive assembly plant costs approximately $1 billion to build with 300,000 units of annual capacity. Tesla's claiming they can achieve similar output with $500 million in capital expenditure. And the Model 2 is the first vehicle designed exclusively around this methodology. But here's where it gets interesting for markets like California, Texas, Florida, and New York, the states that represent over 40% of US EV adoption. The unboxed process enables radical localization of production because module assembly requires less specialized tooling than traditional stamping and welding operations. Tesla can theoretically establish smaller regional manufacturing hubs that serve local markets with reduced logistics costs. A Model 2 built in Texas for Texas buyers eliminates cross-country shipping expenses that currently add $800 to $1,200 to vehicle delivery costs. When your target price is $11,555, every $1,000 matters exponentially more than it does on a $100,000 Model S. The profit margin equation is where this gets really technical. Tesla's average roughly 25% gross margins on vehicles, industry-leading but achieved on premium products with average selling prices above $50,000. To hit $25,000 retail with similar margins, they need manufacturing costs of around $18,750. Traditional EV production at this price point loses money. Even Chinese manufacturers like BYD operate on 15% to 20% margins on affordable models. The unboxed process potentially closes this gap by reducing labor costs per unit by approximately $3,000, facilities costs by $1,000,